This is the 22nd video in a series devoted to complex analysis. In the last video, we looked at residues of functions, and today we want to look at something called the Cauchy residue theorem, which links residues to the integral of functions over certain regions. And this is where I think complex analysis gets really fun because, as you'll see in some upcoming videos, we're able to tackle, some really interesting real integrals, so integrals of real valued functions using complex analytic methods. And those methods are really beautiful. And we're starting to build some of those methods right now. Okay, so let's recall some of the stuff we did last time. So if we've got the following Laurent expansion of a function f of z, so it's the sum as n goes from z, so n goes from negative infinity to infinity over all integers of a sub n z minus z naught to the n, where this converges in a punctured disk centered at z naught. So z naught could be some sort of singularity here, if you will. Although if it's not a singularity, it also converges when this z minus z naught is 0, and you only get non-negative powers of this z minus z naught. Okay, then we define this notion of the residue of f at z naught to be a sub minus 1. So that's the coefficient of 1 over z minus z naught in this expansion. And by the Cauchy integral formula, or by some version or some extension of the Cauchy integral formula, that was equal to 1 over 2 pi I, and then the integral over a circle centered at z naught of radius little r, where that little r is less than big R, of the function f. Then we also define something called the residue at infinity as negative the residue of 1 over z squared times f of 1 over z at 0. So this is kind of a standard way in complex analysis to define things at infinity by doing some sort of transformation of the original function where you push the number 0 to the number infinity and vice versa. I'd like to also point out that we had several tricks or shortcuts for calculating the residue in our previous video, which we will use today, but I won't explicitly review them. So make sure to check out video 21 if you need to review those tricks. Okay, so we're going to start with our big theorem and then look at some examples. And like I said earlier, that big theorem is called Cauchy residue theorem. And what we want to start with is a function which is analytic on a domain D and its boundary del D, except at a finite set of isolated singularities. We'll name those singularities z1, z2, all the way up to zn. And those lie in D, so not on the boundary, so in the interior. Then the integral over the boundary of f of z dz is equal to 2 pi I times the sum of all of the residues at those singularities. So that's what we have here. The sum as j goes from 1 to n of the residue of f at zj. Okay, nice. So this proof is actually pretty simple, but it's only simple because we have a lot of machinery behind us. Okay, so let's see how it goes. So we're going to start by taking some epsilon bigger than 0 such that all of the disks centered at these singularities of radius epsilon are contained within D. So this is most definitely possible because there's a finite number of them. If you want to do it more explicitly, you could take an epsilon 1 so that the disk of radius epsilon 1 centered at Z1 is contained in D, and an epsilon 2 and up to an epsilon n, and then just take the minimum. And we're guaranteed to have a positive minimum because we have a finite number here. Okay, so anyway, such that the set of all z, such that the modulus of z minus zj is less than epsilon, is totally contained in D. So like I said, we can do that because of a finite number of things here. But we want one more condition on epsilon, and that condition on epsilon is that it splits these apart from each other by at least epsilon. So in other words, all of the zj's are at least epsilon away from each other. So we can encode that as follows. So and maybe the modulus of zj minus zk is bigger than or equal to epsilon for all j not equal to k between 1 and n. So let's get a picture of what's going on there. So we've got our picture here. Let's say this is our region D. And let's put some singularities in there. So maybe that's our singularity Z1. This over here is our singularity Z2. This over here is our singularity Z3. And we might as well do this over here being our singularity Z4. So our epsilon has two conditions. One condition is if we put an epsilon bubble around each of these, we land inside of the region D. Another condition, which is given by this, is that none of those bubbles intersect. So that picture would look like this. We've got this bubble right here. So it's inside D, and it doesn't intersect with any of the other bubbles, like, for example, this bubble here, or this bubble here, and it doesn't intersect with any of them. So this is obviously the case when n is equal to 4, but that's okay. So next up, what I'd like to do is define a new space, and that new space will be called d epsilon, and it'll be d minus all of these bubbles. So I can write that as d minus the union as j goes from 1 to n of all of these sets right here. So this is going to be all z such that the modulus of z minus zj is less than epsilon. And like I said, that's going to be everything except for these bubbles. So I'll maybe shade that in this blue color. So there I'm shading everything outside of these bubbles blue. This is going to be our d epsilon. Maybe the most important thing about this construction is that we've removed all of the places where f has a singularity. So that means that f is analytic on this d epsilon space. And now let's orient the boundaries kind of in an obvious way. So we'll orient these boundaries this way. So the boundary of D is oriented positively. So when I say oriented positively, I mean when we walk around it, the region D is to the left. And then all of these are going to be oriented in this clockwise orientation. And that's because if we walk around these, the region is to the left as well. Okay, good. So now we can calculate the integral over the boundary del D of f of z as follows. So that's going to be equal to the boundary over the region del D epsilon. So that boundary is going to be made up of this boundary right here, as well as all of these boundaries right here. And so that's going to be everything except for the bubbles is bound by this D epsilon here. And so of f of z dz, but then that's included more boundary than we actually have for our region D. So we need to subtract that off. But by reorienting these circles the other way, so maybe I'll do that in a different color. Maybe I'll reorient them this way in purple, which is the standard orientation for if we are integrating the insides. We can see that we can just sum up the integral over all of these boundaries of these bubbles. So that's going to be equal to what? The sum as j goes from 1 up to n of the integral over z minus zj equal to epsilon of f of z dz. So something like that. But now, given that f is analytic on d epsilon, we see that this thing goes to 0. And then notice we've got all of these integrals right here, which are exactly the residues. Well, they're not exactly the residues. They're 2 pi I times the residue, which is what we get from multiplying this 2 pi I over. So that gives us this is equal to 2 pi I times the sum as j goes from 1 to n of the residue of f at zj. But that's exactly what we wanted to show. Okay, so now that we've got this kind of setup or this setup theorem proven, let's work through a couple of examples. Now we're going to look at the integral of 1 over z times z squared plus 1 over a couple of different contours. So this first one loops around 0 and I, and the second one loops also around minus I. And that's important because it's pretty easy to see what the singularities of our function are. So 1 over z times z squared plus 1. So those are going to be 0, I, and minus I. So we get 0, obviously, from that z in the denominator, and then we get plus or minus I because of this z squared plus 1 in the denominator. These are both roots of that z squared plus 1. So this gives us motivation for finding residues of our function at each of these points. So let's do that. So notice that the residue of, let's see, f, or 1 over z times z squared plus 1 at 0 will be equal to, since it's a simple pole, we can take the limit as z goes to 0 of z times this. But if we multiply this by z, it just cancels the z in the denominator, giving us 1 over z squared plus 1, or the number 1 in the end. So that's our first residue. Now let's find the residue at I. So the residue of 1 over z times z squared plus 1 at I will be equal to the limit as z goes to I of z minus I multiplied by this function. But that's going to give us 1 over z times z plus I. Given the fact that z squared plus 1 splits into z plus I and z minus I. So now evaluating this at I, we'll get I times 2I in the denominator, but that gives us minus 2 in the denominator, which gives us, let's see, the number minus 1/2. Okay, good. Now let's do one more. Let's do maybe the residue of 1 over z squared plus 1 comma minus I. So the residue at minus I, because that's another one of our poles in this case. And that's, again, a simple pole. So this is going to be the limit as z goes to minus I of 1 over z times z minus I. But again, that's going to give us minus 1/2. Okay, good. So now we have all of our residues calculated. And since we have all of our residues calculated, it should be fairly routine to calculate the two integrals that we want to. So notice that since this boundary of D1 encircles 0 and I, this is going to be equal to 2 pi I, and then the residue of 1 over z times z squared plus 1 at 0, plus the residue of 1 over z times z squared plus 1 at I. Again, because we're encircling 0 and I. So this gives us 2 pi I. And then we'll have 1 plus -1/2, but that's going to give us half. So in the end, we get pi times I. So that's the value of this integral. Notice the interesting thing here, it doesn't really matter what shape this pink circle is. All that matters is that it encloses 0 and I. It could do something crazy like loop way out here and way back here. But since it only encloses 0 and I, we can apply this theorem as we did. Okay, so let's do the other one. So let's take the integral over the boundary D2 of 1 over z times z squared plus 1. That'll be equal to 2 pi I times the sum of the residues at all of the points, because it encircles all of them. But that's going to give us 1 plus -1/2 plus -1/2. That'll cancel out, giving us 0. So in the end, we see that this integral is equal to 0. All right, let's move on to the next one. For our next example, we'll look at the integral over the circle centered at the origin of radius 2 of the function z squared plus 4 over z squared times z plus 1. So let's get a picture of this contour first. So there we've got our complex plane. Here we've got the point 2. The point -2 is over here. The point 2i is here, and the point -2i is here. That's probably more than we need, but it's useful to be kind of complete here. Then we'll draw this circle, or we'll approximate a circle at least. So here, this is our space where the modulus of z is equal to 2. I guess maybe I'll put a little circle here to show that we're integrating over the whole thing. And now let's look at where our poles are, or our singularities, which happen to be poles. So notice we have a double order pole here at 0. That's because we have z squared in the denominator. And we have a single order pole at z equals -1. That's because we have this z plus 1 in the denominator. So let's write that out. So double pole at z equals 0, simple pole at z equals -1. But that means that when we calculate this integral, it'll be 2 pi I times the residue at the double pole plus the residue at the simple pole. So let's see what that gives us. So like I said, 2 pi I times the residue of our function z squared plus 4 over z squared times z plus 1 at 0 plus the residue, same function, z squared plus 4 over z squared times z plus 1 at -1. But now we'll use the strategies for calculating residues at double poles and simple poles. Let's recall the strategy for calculating the residue at a double pole is to take the limit as z goes to 0 of z squared times the first derivative of this thing. So that's just a shorthand of the rule that we calculated in the previous video. Again, I'll let you guys look that up if you need to. Okay, so in the end, that gives us 2 pi I. Then we'll take the limit as z goes to 0. We multiply this by z squared. That gives us z squared plus 4 over z plus 1. And then we need to take the derivative of this as well. And so, good. That'll be our residue at 0 because it's a double pole. Okay, then next we take the residue of the simple pole at z plus 1, but we can do that the same kind of way that we did before. So that's going to be the limit as z goes to -1 of z squared plus 4 over z squared. So something like that. So we really multiplied by z plus 1 and then took the 0th derivative. But now we can take the derivative of this guy using the quotient rule. So let's see what that'll give us. That'll give us 2z times z plus 1 minus z squared plus 4 over z plus 1 squared. So like I said, that's the quotient rule. And then we need to plug in z equals 0. So it's just a valuation because we've got a function at this point that's continuous at z equals 0. We don't have to think too hard about it. But then this one is continuous at z equals -1, so we can just plug it in and we'll see that we get 5. So I'll just put plus 5 here. Finally, when we evaluate this at z equals 0, we see we get -4. So I'll let you guys work out the arithmetic, but that's pretty straightforward. So in the end, we get 2 pi I times -4 plus 5, but that gives us 2 pi I. So for our next example, we'll do exactly the same integral, but we will use the so-called residue at infinity method. So let's recall that this thing has singularities at z equals 0 and z equals -1, which I've drawn here inside of the circle of radius 2. So before, we oriented this thing counterclockwise, meaning that we would get the residues of all of the things in the center. But if we instead orient this thing counterclockwise, we'll get the sum of all of the residues outside of this circle. And that's because that if we orient this thing counterclockwise, the region that this is enclosing, if you will, is everything outside of the circle. So it's like this kind of actually neat looking sun shape. Okay, so that means here we have negative, and it's negative because we're orienting it the other way. So this thing is kind of standardly oriented counterclockwise. So if we change the orientation, then we need to put a minus sign to kind of fix that. And then we'll have 2 pi I times the residue of our function. So I'll just say so I'll just call our function f at infinity. But let's see, that's going to be equal to -2 pi I times the residue at infinity, but we'll use this for the residue at infinity. It's got a built-in minus sign, which will cancel this minus sign. So that gives us 2 pi I, and then the residue of 1 over z squared, f of 1 over z. So that means we need to do that to this function right here. So let's see, 1 over z squared, and then f of 1 over z. That'll be 1 over z squared plus 4 over 1 over z squared times 1 over z plus 1 at 0. So that residue at 0. But we get a little bit of cancellation here. Notice that if we multiply this z squared through the denominator, it cancels this and this. And then we'd probably like to multiply the numerator and the denominator by z squared in order to make it look more like a nice rational function instead of kind of a clumsy rational function. So that'll give us 2 pi I times the residue of 4z squared plus 1. That's what we get multiplying through the numerator over, let's see, I'll multiply 1z through and keep 1 out. So that'll be z times z plus 1 at 0. So that has a simple pole at 0. So that's good to know. Calculating simple poles at 0 is pretty easy. We can do 2 pi I times the limit as z goes to 0 of this thing multiplied by z. So 4z squared plus 1 over z plus 1. So now plugging in z equals 0 because that's continuous, we see that we'll get 2 pi I because this limit is equal to 1, which is exactly what we had working this out the other way, which is obviously expected, but it's nice to see that this strategy works as well. So I guess the takeaway here is if it's simpler to take the residue at infinity because there's only one residue to take, maybe go ahead and do that if you've got that as opposed to the residue of a bunch of poles or singularities within some region. All right, let's move on to another one. So our next one's a bit different, but I think that's good. It's the integral over the unit circle of z squared times e to the 1 over z. So if you recall, e to the 1 over z doesn't have a pole at 0. It has something called an essential singularity at z equals 0. That means that the powers of z to the minus n, well, they extend all the way negatively. They never stop. So what that really tells us is that the way to calculate the residue here is by actually doing the Laurent expansion. Luckily, since we have e to the 1 over z, this is fairly straightforward. So let's maybe summarize that here. So our function z squared e to the 1 over z, this has an essential singularity at z equals 0, which, like I said, means that we need to look at the Laurent expansion. So z squared times e to the 1 over z will be equal to z squared times 1 plus 1 over z plus 1 over 2z squared plus 1 over 6z cubed plus dot, dot, dot. So let's recall that this is expanding as the sum as n goes from 0 to infinity of 1 over z to the n times n factorial, or maybe n factorial times z to the n. So that's just by the standard expansion for the exponential function. Okay, so now we can multiply this z squared through and see that we get z squared plus z plus 1/2 plus 1 over 6 times 1 over z plus dot, dot, dot. It in fact doesn't matter what the rest of that is because seeing this right here tells us that the residue is equal to 1/6 because that's the coefficient of z to the minus 1. In other words, this 1/6 is our a sub minus 1. But now we can just write down the answer essentially. This is going to be equal to 2 pi I times the residue of our z squared e to the 1 over z at 0, but that'll be equal to 2 pi I times 1 over 6. That gives us pi I over 3. Let's keep going. So for our next example, we'll look at the integral over the circle centered in the origin of radius 4 of z over the sine of z. So I chose 4 because that is larger than pi, but smaller than 2 pi. So let's get a picture of that going on here. So let's put our circle of radius 4 centered at the origin. So it looks something like that. And so we know that sine of z is equal to 0 at all integer multiples of pi. So that gives us something right here, a pole right here, 0. And a pole right here at pi, and a pole back here at negative pi. Like I said, given that this is 4 and negative 4, that's all of the poles contained within this circle because 2 pi is obviously like bigger than 6. That would be out here. Negative 2 pi would be out here. So that means in order to calculate this, we need to find the residue at each of these poles. So let's do that. So the residue of z over sine z at, like I said, maybe z equals minus pi. So what's that going to be? Well, we're going to use a slightly different formula here. So let's recall that if we have a simple pole, which we do, we can find the residue by taking the numerator function, leaving it alone, then taking the derivative of the denominator function and then plugging this in. So that'll be z over cosine of z evaluated at z equals minus pi. So cosine of negative pi is equal to -1. So this gives us negative pi over -1 or the number pi. Okay, great. And then let's take the residue of z over sine of z at 0. So I think maybe in a previous video we showed that this function has something called a removable singularity at z equals 0, which means the residue is 0. But we can use the same strategy that we did before. So if we take this and we maybe take the derivative of the denominator by leaving the numerator the same, again, that's one of these rules for finding the residue at a simple pole that we derived in a previous video. We get z over cos z evaluated at z equals 0, but that gives us 0, given that cosine of 0 is equal to 1. And then similarly, we can calculate the residue of z over sine z at pi is equal to -pi, using the same strategy and the fact that cosine of pi is -1. So now we're good to go. So our final answer will be 2 pi I times the sum of these residues. That'll be equal to pi plus 0 plus minus pi. That clearly all cancels to 0. So that's our final answer here. Okay, let's do another one. For our next example, we'll look at, again, a circle of radius 4 centered at the origin. The integral of this function, e to the z over z squared plus 9 all squared. Okay, well, let's notice that this circle of radius 4 contains 2 poles of this function. So let's draw our circle of radius 4. So it's something like that. So let's say 4 is here, -4 is here, maybe -4i is here, and then 4i is here. And this has poles at 3i and -3i. We can see that because z squared plus 9 factors as z minus 3i times z plus 3i. And then moreover, since it's squared, there are double poles at each of those places. Okay, so that means we've got a double pole up here at 3i. We have a double pole down here at -3i. But those are all the poles or all of the singularities of this function. So in order to calculate this, we have 2 pi I and then the residue of our function e to the z over z squared plus 9 at -3i plus the residue at 3i as well. So let's calculate each of those. So here we have 2 pi I, and then we need to take the limit as z goes to -3i of, let's see, we'll need the derivative with respect to z of e to the z over, this will end up being z minus 3i squared. That's because we need to multiply by z plus 3i squared, which cancels out this z plus 3i squared that we get, remembering that this is all squared within our function. Okay, and then we've got a similar type of picture for the other one. So this is going to be the limit as z goes to 3i, and then we have the derivative with respect to z of e to the z over z plus 3i squared from the same sort of cancellation. Okay, so let's see what we get from that. So this is going to be equal to 2 pi I. Then we need to take this derivative. So that's going to look something like e to the z times z minus 3i squared minus 2e to the z times z minus 3i. And this is going to be all over z minus 3i squared evaluated at z equals -3i and then plus the other one. Okay, so a lot's going on there. Okay, but then that'll give us 2 pi I. Then evaluating this at -3i gives us something like this. We have e to the minus 3i We could pull that out of the whole thing. And then we could do a bit of cancellation. So notice this z minus 3i squared cancels with this z minus 3i squared, leaving us with e to the minus 3i minus, when we do it over here, we're left with 1 in the denominator. So that'll be minus 2e to the minus 3i over, let's see, that'll be negative 6i, plugging this in here, keeping in mind that when we cancel this one, it cancels this down to an exponent of 1. So if we've got a 6i in the denominator, well, it's a negative 6i in the denominator, the minus sign will cancel that minus sign. Okay, and then finally we have plus another one, which looks fairly similar. Okay, well, I think this is probably good enough for this one. There's a bunch of like calculation to go on, but I think the calculation is straightforward. So let's move on to another one. For our next example, we'll look at the integral over a circle of radius 2 centered at the origin of e to the zt, where t is a positive real number, over z squared plus 1. So making our standard picture here, we've got a circle of radius 2, like that. And then notice that our poles are at I and negative I. So we've got a pole here at I and we've got a pole here at negative I. Those are both poles of order 1 or simple poles. So that makes this fairly straightforward. That's going to give us 2 pi I, and then we'll have e to the zt over z minus I evaluated at z equals minus I, plus e to the zt over z plus I evaluated at z equals I. So I skipped some steps there, but that's what we get from multiplying this one by z plus I and the other one by z minus I, and then taking the limit. In the end, we get 2 pi I, and then e to the I times t over, let's see, this is going to be negative 2i plus e to the, sorry, this should have been minus I times t, and then plus e to the I times t over 2i. So something like that, but notice in the end, we get 2 pi I times e to the it minus e to the minus it all over 2i, given the fact that we can bring this minus sign up. But notice that's exactly the sign of t. So in the end, we get 2 pi I times the sign of t, which I think is pretty nice. All right, let's do one more example. So for our last example, we'll look at the integral of 1 over z to the 8 minus 1 around the circle of radius 1 centered at 1. So let's see what picture that looks like. So let's put 1 here, we'll put 2 here. Then we need to put a circle of radius 1, so it looks something like that. Well, that doesn't really look like a circle, but you can imagine that it's a circle. Okay, now let's look at the poles of this thing. So the poles are exactly the 8 roots of unity. So we know that one of the roots of unity will be the number 1. If we plug in z equals 1, well, that obviously goes to 0. And then negative 1 will be another 8th root of unity. And then I will be a root of unity. Negative I will be a root of unity. But then everything along the unit circle kind of in between here will also be a root of unity. So it's going to be all of those points right here, those 8 points. But let's notice that these 3 right here, which I'll color in pink, are the only ones within our region. So that's good. We only need to find the residue at those places. But what are those poles? Well, we have z equal to 1, and then this is z equal to e to the pi I over 4, or I pi over 4, because that's going to be with a angle of pi over 4 from the real axis, just using the standard rule for writing this in polar form. And then we also have one at z equals minus I pi over 4. That would be this one down here. So that means we need to calculate the residue at all of those points. So let's do that over here. So the residue of this thing, 1 over z to the 8 minus 1 at 1. So we used the trick before where we leave the numerator as is and take the derivative of the denominator. We can only do that with simple poles, but we have simple poles. So this is 1 over 8 times z to the 7 evaluated at z equals 1. So in the end, that just gives us 1 over 8. Okay, so now let's look at the residue of 1 over z to the 8 minus 1 at e to the pi I over 4. So that'll be, again, 1 over 8 z to the 7 evaluated at z equals e to the pi I over 4. So that gives us 1 over 8. And then e to the, let's see, that's going to be 7 pi I over 4. And then similarly, the residue at the other point, 1 over z to the 8 minus 1 of e to the minus pi I over 4, will be equal to 1 over 8 times e to the minus 7 pi I over 4 for similar reasons. Now let's notice that 7 pi over 4 is down here. That's exactly e to the pi I over 4. So we can replace this in the denominator with e to the pi I over 4. Similarly, we can replace this in the denominator with e to the pi I over 4 because of the same reason, just going around the other way. Sorry, this should have been a negative pi I over 4. Going around 7/4 of the circle this way is the same thing as going around 1/4 of the circle back this way, and vice versa. So in the end, we have, for this integral, we get 2 pi I times the sum of these residues. Maybe we'll bring this 8 out front, and then we'll have 1 plus e to the pi I over 4 plus e to the minus pi I over 4. Next up, we can use the fact that these kind of have nice expansions. This one is 1 over root 2, and then 1 plus I. This one right here is 1 over root 2, and then 1 minus I. So in the end, the imaginary parts cancel, and we're left with pi I over 4 from simplifying this. And then we'll have 1 plus 1 over root 2 plus 1 over root 2, so that'll be 1 plus 2 over root 2, but 2 over root 2 is exactly the square root of 2, so that gives us pi I over 4, and then 1 plus the square root of 2. So that's going to be this integral. Okay, I'll leave you guys with some warm-ups. So for your warm-up, I've got these 3 integrals that we'll evaluate using the Cauchy residue formula. So the first is the integral over a circle of radius 2 centered at the origin of sine of z over z squared minus 1 squared. The second is over the same circle, but now z squared over cosine of z. Finally, the last one is over the circle of radius 3 centered at the origin of sine to the 6th z over z minus pi over 6 cubed. Okay, that's a good place to stop.